So if you guys go to the JuliaEO repository and git clone, you should be able to, in one of the directories, see, let's see if we go here, we see notebooks. You can see that I just pushed it, day 4, and you'll have a score-based diffusion tutorial. And that's going to be basically what we're going to go through in this little session here. So before jumping straight into the code, just to give you at least a little bit of background on what you're going to be doing and looking at, I want to give a brief overview of score matching. So this is let's say the stochastic equivalent of what was shown by Alexander earlier on finding a flow field. But let's say the stochastic version of a flow field. And the way that it works is actually pretty elegant and subtle. So it's not obvious how all the things that I showed before in terms of generating new images, how that really works underneath the hood. And I hope to unveil that a little bit with this tutorial. So the starting point is that you represent your data set as an empirical distribution, as shown here. What this distribution represents is if you have some data set, it just means that you just pick out one of your images at random uniformly. So if you have 10 images in your data set, this distribution says, okay, pick a number 1 and 10. If you get 3, you draw the third image. And so that's the first representation of our data. The next step, and this is where diffusion models get their name, is that you add noise to these delta functions. So if you have an image, you add Gaussian white noise to every single pixel. And that data distribution instead, not just the original image, but the corrupted noise version of the image, which is now generative, because you take an image, there's many different kinds of random noise that you can have now, is represented by the following Gaussian mixture distribution. Okay, so first step, just take your data, think of that as an empirical sample. Second step, corrupt it with noise. And you see there's a sigma there. That's the amount of noise you're using to corrupt it. So as sigma goes to 0, you produce your empirical distribution. But the power of generative models is that you always have this regularization parameter. And it's critical to getting anything to work. And here we get to the score function. So the score function, this mysterious thing from the score-based diffusion model, is just the gradient of the log of this probability density. And because we wrote it down, it's a sum of Gaussians, we can actually write down the score function analytically. And then what we do is we minimize the discrepancy between this analytic formula and a neural network. Now, the first thought you may have is we have an analytic formula for the score function. So why do we need a neural network at all? Like, we already know the answer, we wrote it down. And the reason is subtle. It's because this function here is very wiggly and very irregular, whereas neural networks, when they tend to learn a function, they start off smooth and then they add complexity later. And this whole procedure of training a neural network from going from something very smooth to something very irregular when you overfit data needs to be stopped at a special time in order for you to get, let's say, the most parsimonious solution to the optimization problem. Okay, you need to avoid overfitting. And it's this avoiding of overfitting is the reason why neural networks work so well at producing new data samples. Neural networks don't just produce your original image with noise added on. They produce new things. And part of that is because of this implicit regularization. Another subtlety is that you don't minimize the discrepancy between your neural network and that analytic formula. What you do is instead create a stochastic formulation of the same optimization problem. And that's because, well, with neural networks, apparently adding more noise makes things better from optimization. You find smoother things sooner. So this is another subtlety. Just to give you an example of what I mean by those different functions and what the neural network actually finds, here I'm showing an example of both the exact solution to the minimization problem, which is that Gaussian mixture, the sum of Gaussians, an exact score function, as well as what the neural network finds when you train it sufficiently well. So I'll describe what the different curves are. The red curve is the exact solution to the score function. So for one dimension, it turns into just a one-dimensional function. In 2 dimensions, you're finding a vector field. And for images, you're finding an operator like a Laplacian or biharmonic, etc. So the analytic score function is the red. The wiggly orange thing is the exact minimizer to the denoising score loss, the thing that the neural network is trying to find but never does. And then the blue curve is what the neural network actually finds when you do the gradient descent on the data. And you see that the blue curve is closer to the red one than the wiggly orange one. And that's part of the magic of why diffusion models work. It doesn't actually find the minimizer, but finds something actually closer to the thing that you actually want. So it's very subtle why these things work. Okay, so the other thing, because one of the themes of this whole workshop is generative AI and various aspects of generative AI. And in the JuliaEO notebook here in this section, the first things that you have to do is you have to first change into wherever you store the directory, go in the notebooks, go to day 4, and then go into the score-based diffusion tutorial. You have to do Julia-project, and then you instantiate the project to download all the packages. And there are a few packages here just to start running. Oh, yes?
I had some issues with 1.12.
Mm-hmm.
So maybe it's better to use 1.10.
Yeah, oh, thank you for the suggestion, Alexander. Yeah, please use 1.10 for this tutorial. I think even 11 probably doesn't work because of enzyme. Yeah, so that's a great tip. So make sure you're using Julia version 1.10 when you're doing the instantiation for this repository.
Enzyme doesn't work beyond 1.10?
Oh, no, it works beyond 1.10. It's just that the syntax changed and some things broke in 1.11 and 1.12. So yeah, they're still figuring out exactly. I think in 1.13, everything's going to be good, but...
No, they're figuring out 1.12 now, so it'll be maybe like a month or so more.
Okay.
Mostly there.
Yeah, I remember, I think there was like some breaking changes that would only happen in 1.13 for like the real fixes, but yeah.
I can see that you have included 2 versions of the file, one with logs and
Yes.
one that seems to be using enzyme. Can I run the example with logs on 1.12?
I think the 1.12 will work with Lux. I think that should all work because that's Zygote and Lux together as opposed to Enzyme with a custom neural network. So that should be fine. Any other questions about Julia versioning and sadness that comes when things break? Right, so instantiate and make sure Julia 1.10 is the safest one to use. And everything should kind of go through.
Maybe one comment. Should people do this in a temporary environment, or assuming they might have to touch other things?
Yeah, this is why I always, here I changed into the directory and I did Julia-project. Because I have a manifest and a project.toml in here. So that makes the whole environment containerized. Yeah. Yeah, so yeah, and instantiate in Julia 1.10. As you see, I'm using version 10.10 here, and everything seemed to be fine. Okay, a little bit about the directory structure and the use of generative AI. So you see there's a bunch of files here, but then there's a README. This README was completely generated by just asking an LLM to generate a README for the repository. And it doesn't say the version 1.10 thing, but overall, the README is actually pretty good at just describing what's inside the repository, how to use it, and, well, what all the supporting files are, dependencies, etc., and even how to install. So, part 1, README for this completely generated with Composer. Part 2 of what I'd use generative AI for. I also put the prompts here, by the way. So like the README prompt was just, can you create a README for this directory? So that's one prompt. The other prompt you see here was to create the Jupyter notebook that you see. And this was done in one shot. I didn't have to do any corrections. And we'll use the Jupyter notebook here to go through the tutorial. And yeah, I did it in one shot, and it looked right to me. This was using Opus 4.5 to generate the notebook. So for this tutorial, we'll use this notebook. All of this generated with one prompt and that prompt that I showed with all the math and everything. Welcome to the new world. So it also describes the dependencies, the main libraries that I'm using here, like GLMACI, progress bars, linear algebra, HDF5. Let me actually minimize this for a second here. And a random seed for reproducibility, because that's always good to have at the top of your script. Oh, make it larger? Yeah. Is that better? Yeah. OK. Thank you. And Shift-Enter to run a cell, and voila, you see this. This simple networks.jl is a custom implementation of neural networks in Julia using more primitives, so not using LUX. And this is just to show that just by building things in Julia, it's actually very easy to do whatever you want. And this is one of the greatest flexibilities of the Julia programming language, just how easy it is to build your own things. And the reason that makes it so simple is because we have a tool like Enzyme that can automatically differentiate through code. So if you want to take a look at how I implemented a neural network just using structs and a few definitions, that's all under simplenetworks.jl. The other reason why I'm using it is actually turns out to be twice as fast as LUX for this example. Because it's simpler, it tries to do less. So as mentioned before, what is a score function? It's the gradient of the log of your probability density. But when you have empirical data, you don't have a continuous description of this probability density. So what you need to do is have some kind of data-driven estimate of this. But because I also was in the process of generating the data, I could actually choose analytically what the score function was and draw samples from this distribution. And so the target distribution that we're going to be trying to learn in this little tutorial in this case is given by this potential function. So, and this potential function leads to this probability density. So in other words, the score function is, if you're familiar with statistical mechanics, it's the gradient of your Gibbs potential, or the gradient of this potential function is what the score function is in this case. And I chose it to have a particular form. Yeah, I actually didn't check to see if the derivatives are right in terms of what I actually wrote as my potential function, but yeah, it looks OK. Yeah, it's actually right. That's fun. OK, so here's the exact score function. This is the thing that we're going to try to find. And I already have a data file with all the data samples generated from this distribution, so you don't need to redo that. But also in the repository, if you want to choose your own potential function and create your own samples, that's in the generate function there as well. So the other thing that I have here is this Gaussian mixture score. And this is that wiggly line that I showed before. This Gaussian mixture score is the exact minimizer of the denoising score loss that we'll see here. So if I choose a neural network that's exactly this function here, it should have a lower loss. That's the intuition. So the challenge is that we want to match our neural network to this gradient log. But the issue is, of course, we only have empirical samples of our data. So what do? And we use this trick from denoising score matching where we essentially regularize it with noise, rewrite things a bit in terms of stochastic sampling, and ultimately minimize the denoising score matching objective down here. So you see it's just an L2 loss. So keep in mind, we know everything here now. We plug in. We first draw a sample from our data. That's X. Or it could be an image in higher dimensional setting. So we draw an image. Next, we choose a noise level. In this tutorial, we'll have a sigma equals 0.05 as our noise level. And then we draw a multivariate Gaussian. So we draw two things, one data sample and one multivariate Gaussian. And then we minimize the difference between our neural network and the noise. There's a bit of math that goes between what I showed before and here, but it is actually just math, which is nice. Like, it's not magic. You derive this loss function. So we have this Gaussian mixture loss function as well, just to show this. When we find our neural network, we're going to compare it to the loss function given by the Gaussian mixture. Okay, so here we can read our data. So that's this part over here. So we loaded 10,000 samples of our two-dimensional data. And we can look at what the distribution looks like. And here I'm using GL-Mackie, so it doesn't show up inline. But this is, roughly speaking, what the distributions look like. Here it's for the X1 distribution, it's the X2 distribution. They're actually correlated, so they aren't independent from one another. And we'll see that a little bit later. But you see it has this kind of bimodal peak, kind of strangely sampled. And this is the probability distribution that we're going to try to learn or to sample from with a neural network. So then we have whatever our Gaussian mixture score says for the origin. You see it gives this kind of crazy answer for one of the origins. So this should already be a hint that this Gaussian mixture score is way more irregular than the exact score that it was sampled from. Okay, and then the neural network architecture. So we've talked about the loss function. We've talked about the data set. And we also need to figure out, okay, what kind of neural network architecture are we going to build in order to minimize that loss? And here I have essentially a feed-forward neural network with linear bypass. If you don't know what that means, it doesn't quite matter. It's basically just a multi-layer perceptron or one of the most basic types of neural networks that you can define with a swish nonlinearity. So the input dimension is two-dimensional since you have an X1 and X2. The hidden layer dimension is 50, and then the output dimension is 2 as well, because a score function takes in 2 inputs and 2 outputs. If you have conditioning, then the input and outputs are different. But here, it's an unconditional generation. So in other words, I'm not taking into account the free surface height if I'm using language from before. So okay, we can define our neural network here. So that's done. And we can create some convenience functions. Okay, so we have our initial loss here. So then we train our network, and we do this with an atom optimizer. Again, everything written by hand in that simple networks function. So these are all things that you can inspect very easily. A certain batch size and keeping track of the loss list and test loss lists. I'm going to run this for 200 epochs. So do that now, and we see that it's training. And I chose a small number of epochs just to make things go by in a snappy manner right now. Okay, so it's trained. You can look at the training loss, which, if I remember, isn't very informative. Yeah, I should probably make them lines instead of a bunch of scatter plots, but the point is that the red dots and blue dots are somewhat close to each other. If they were very far from each other, then it would be a bit more suspicious. Okay, and now we can evaluate our losses here. And yeah, so our neural network, this is a much better evaluation than I had before, got a loss of 800. The actual value doesn't matter, but the relative values does. So the network is 800. The Gaussian mixture loss, as I promised, is actually a minimizer of the loss function. So in principle, this is the smallest value that it can be. But because of stochastic sampling of the denoising score loss itself, it's not necessarily the case. And then the exact score loss is 810. So the point is that the function that we're actually trying to find has a higher loss than the minimizer of the loss function. It's something to wrap your head around if you're used to actually wanting to minimize the function that you write out. Okay, because we're in 2 dimensions, the score function is a vector field. Mapping two positions to 2 outputs can be visualized as a vector field. So we can see how close the learned score is to the analytic score is to the Gaussian mixture score. So the first ones are just some evaluations for plotting. And we can take a look at the different vector fields. So the neural network learned the vector field on the left. The Gaussian mixture field. Basically, it looks like a bunch of little arrows. Essentially, the little arrows almost point to each data sample that you have. So visually, you can almost see where those 10,000 points are sampled. And then the one on the furthest right is the exact score field. The point is that the neural network doesn't exactly look like exact score field, also because we just didn't train long enough. But it does have one important feature, which is, and I'll say this out loud here. You see that a bunch of things are converging over here. And you see that a bunch of things are converging over here and mirrored down here. The neural network is missing those points, but it just hasn't been trained long enough. There aren't a lot of data samples in those regions. But nonetheless, we'll see that even if it's not doing it perfectly, a lot of the statistics are matching quite well, even with this score function. And that's because score functions are the gradient of the log of your probability density, and learning a gradient is harder than learning the actual probability density. So when you draw samples for something that's, let's say, incorrect, because you actually care about it integrated, it smooths it out a bit, so you don't need to be exactly correct with a gradient of the log of the probability density. And we can also look at the heat maps of the score function, just to take a look at the vector field in a different way. And we see that, maybe I need to change the plotting ranges a little bit, but it's roughly dark where it should be, roughly light where it should be. It doesn't have very many samples at the very edge, so it's going to get the tail statistics wrong. That's what it means to be wrong at the very extreme points, like x equals +2 or -2. And then comes the sampling part. So now we have our score function, we have this vector field. How do we draw samples from it? And there are many ways to draw samples from it. One was similar to the one that Alexander mentioned earlier, where you try to create this mapping from a distribution you like, typically multivariate Gaussian, to the distribution that you want, something coming from your data. And that's one way. And in the context of diffusion models, that's the reverse diffusion process, which can also be reformulated as a flow matching problem as well. So you can also do it deterministically once you have the score function. But another way to draw samples is actually just to evolve this stochastic ODE forward in time. The reason why people don't do this in practice is because it just takes longer to draw independent samples. So the reverse diffusion is a more efficient way of drawing samples from the data distribution you care about. This works, but it's more inefficient. And here I'm doing the typical stochastic ODE hack of where I take the deterministic part to be Runge-Kutta 4 and then just slap on the noise at the end. And this is a nice stable way to run a stochastic ODE forward in time. And then, well, we can run our Langevin equation forward, draw some samples. Let's see, how many samples am I drawing? I'm drawing 1,000 samples after 1,000 time steps of time step size delta t equals 0.1. And then I can compare the distributions. And here there are some caveats. Again, I didn't write any of these caveats here. These are all generated by Claude. But, it's roughly the right things to look out for. And I can look at the samples generated. And you can see that the original is in the red, so the overlap purple is what we're trying to get maximized. And then the generated samples are in the blue. So it doesn't quite capture the bimodal structure, but you can just by eye see that the mean and variance are probably about right, just by eye. So that's another thing that you learn about using these diffusion models. They tend to get lower order statistics right first and then higher order statistics right later. And we'll see that quantitatively in a second. So if we actually look at the mean and covariances of our generated model versus the original exact data set, we get the original mean should be 0, but because of finite sampling effects, it's about 0.01. You see that the diffusion model is about an order of magnitude higher in terms of that, but again, also less samples, so that might be a part of the issue. But the generated covariance of the diffusion model, if you just look at those numbers in the matrix, are actually pretty close to the covariance of your data set as well. So the variance of the x1 variable was about 1.2, and you see that the neural network gets the same value. And the anti-correlation between x1 and x2 is also captured. Negative 0.5 is what the neural network produced, and the original was around 0.4. So even with this super fast training, very small network, and let's say expedited little hands-on tutorial here, we see that score matching can even be done on the CPU very quickly for these low dimensional distributions. So to review, what we learned was what the score function was, what denoising score matching is, how neural networks can approximate the score function, and how do we use Langevin dynamics in order to do the sampling. There are several extensions that people can do, including the reverse diffusion process. But overall, this gives you kind of the basic ideas of what score matching is, how it's done in practice, and then doing further extensions to images or conditional distributions is a straightforward extension of what you've seen here. And with that, I'm happy to take any questions on, well, either running the code or anything about diffusion models in general.
Thanks, Andre, for this great tutorial. I was wondering, so I'm more familiar with DDPM, denoising probability distribution, DDPM, okay. And I'm wondering if the score matching approach is a mathematical reformulation of the same approach, or
It
is it? It is. Is it so? So mathematically it's equivalent, but
Yeah.
in practice it's different, or?
Yeah, it's one of these things where, yeah, it is mathematically equivalent. If you take your score function and you rewrite it as like a negative x plus score function, you get that version of it. So it's just like a affine transformation of what the score function is in order to get the DDPM.
Okay. Okay.
Yeah.
So and the additional thing of the score is that you have
Yeah,
this
it's
new
like a
interpretation?
x plus score or negative x plus score is if you just rewrite things that way, like your score function equals negative x plus neural network, instead of trying to get the neural network to directly represent the score, then you get the other formulations.
Okay.
And then there's affine combinations of them that look very similar to the flow matching that you've done as well.
Okay, great. Thanks.
Oh, and to answer the question of why people formulate it differently, yeah, the optimization procedure is like sometimes you get better answers when you formulate it slightly differently. There was a paper in 2022 where, I think Harris, 2022, where they explored the design space of how you do score matching. And eventually they decided like essentially a linear combination of this method plus the DDPM method is like the one that gave the best answers for image generation. That was more empirical, saying like, okay, for the examples we looked at, this seems to be the best combination. Yeah, and you can also play tricks to minimize the number of times you evaluate the reverse diffusion process in order to draw a very good sample. Yeah, the more the better, but like you can reduce it down to like 20 evaluations of your neural network. Any other questions? All right, if not, I'm here if you guys have any more questions about score matching or anything else. Oh, the connection to client models, I should probably mention that. Yeah, the atmosphere is basically noise, so that's the connection. We think of the model that we have here as the ocean model, and the noise is the atmosphere. This was a Hasselmann's approach to climate modeling way back when. And so these stochastic differential equations are very tied to simplified versions of how we think of the climate. But yeah, if anyone has any more questions about any of this, happy to answer them. Point to more sophisticated repositories to do, let's say, image generation, all in Julia, as well as other tool sets that you might use in order to, or other uses of score matching aside from generating samples. Thank you.